The next thing we're going to look at when it comes to naming ionic compounds and writing their formulas, we're going to look at what to do with polyatomic ions. Polyatomic ions are ions made up of more than one atom. More than one atom, and that cluster of atoms is covalently bonded together. So polyatomic ions are kind of funny because you've got an ionic compound, but the little cluster in the polyatomic ion is covalently bonded together. Polyatomic ions always contain nonmetals, and they may sometimes contain metals. They are listed, the ones you need to know are listed alphabetically on the back of your periodic table. And they have special names, and those names often end with ATE or ITE, ate or ite. When you name compounds that contain polyatomic ions, it is important to use the name as it is shown on the back of your sheet. Do not change the name. Don't try to change the ending to IDE. Here I've shown you 4 quite common polyatomic ions. Ammonium is special because it is really the only positively charged polyatomic ion you're going to need to use in this class. Hydroxide is special or noteworthy because it does not have that special ending ate or ite. It has the kind of normal ending IDE that all the monatomic ions have. So you just kind of need to remember that special name. When you see hydroxide, know that it is a polyatomic ion. So you have to look on the back of your periodic table for that one. Carbonate and phosphate are 2 of your more typical polyatomic ions with that ate ending. And notice that a lot of, with that ate and ite ending indicates that you have an element that's bonded to a lot of oxygens. So you see a lot of oxygens in polyatomic ions. For my honors students, you are going to need to memorize some of your polyatomic ions. So I just wanted to draw your attention to some naming patterns with your polyatomic ions. So the most common ion ending will end ATE. We'll have that ate ending. And if you remove one oxygen from the ate version of the ion, you end up with the ite version of the ion. So an example of this would be nitrate versus nitrite. Nitrite has 1 fewer oxygen than nitrate has. Then, if you remove 1 oxygen from the ite ion, you add the prefix hypo in front of the name. And if you add 1 oxygen to the ate version of the ion, you add the prefix per in front of the name. So an example for the full series would be going from, the most common version is chlorate with 3 oxygens, but we start off with hypochlorite, has the fewest number of oxygens, then chlorite with the next fewest oxygens, then chlorate, and then perchlorate with 4 oxygens. So this is kind of a naming trick to help you remember more of these polyatomic ion names. All right, back to everybody. In Chem 1, I am only going to ask you to name fairly simple compounds. So if I give you a compound that has more than 2 elements in it, the reason why it has more than 2 elements is because it has a polyatomic ion. So if you see anything more complicated than just like HCl or NaBr, if you start to see something like NH4Cl, you've got 1, 2, 3 elements in that compound, and therefore you know it contains a polyatomic ion. Okay, but our naming rules are the same as they have been. We just name the cation and we name the anion. So this is sodium with the hydroxide ion. Sodium ion and a hydroxide ion, so we just call it sodium hydroxide. Oops, I'm writing the symbol. Sodium hydroxide. Here we have this ion, NH4, which is ammonium. Ammonium is NH4 with a charge of +1, and the oxide ion with a charge of -2. So we just call it ammonium oxide. Here for this next one, we have gallium ions pairing up with sulfate ions. So we have gallium sulfate. This sulfate ion is SO4 with a charge of -2. And here we have calcium sulfite, because we have calcium ions pairing up with the sulfite ion, and the sulfite ion is SO3 with a charge of -2. Calcium sulfite. When it comes time to writing the formulas, the same rule that we've followed for all ionic compounds up to this point apply. Charges must add up to 0. There's just a new trick here. We use parentheses if there is more than one of a polyatomic ion in a formula. So if we go back to the previous slide, look here. I used parentheses around the ammonium ion when I had 2 of them. I used parentheses around the sulfate ion when I had 3 of them. But when I just had one sulfite ion, I did not use parentheses. And when I had just one hydroxide ion, I did not use parentheses. Therefore, like with calcium hydroxide here, I have one calcium ion, but I need 2 hydroxide ions in order to have a total negative charge of -2 to balance out the +2 charge from calcium. So the correct formula is calcium hydroxide with the hydroxide ion in parentheses with the number 2 outside to let me know that I have 2 of this entire polyatomic ion. As I've already said, you do not use the parentheses if there is only one of the polyatomic ion in a formula. So for ammonium nitrate as an example, these charges balance out as they are, one positive, one negative. Therefore, I just need one of each ion, so I just write NH4NO3, no parentheses. So let's try some of these examples. Potassium chlorate, I have potassium ions and chlorate ions. Be sure you copy down the formula carefully off of the back of the periodic table. Make sure you're looking at chlorate, not chlorite. It's easy to make that mistake. And then those ions pair up in a 1-to-1 ratio, so this formula does not need parentheses, it's just potassium chlorate. For magnesium nitrate, we have magnesium ions with a charge of +2, nitrate ions with a charge of -1. So I need more negative ions. I need a second nitrate ion. So this formula will need parentheses because I have 2 nitrate ions. And the correct formula is MgNO3, 2. For ammonium carbonate, ammonium ions have the formula NH4 with a charge of +1. Carbonate ions have a charge of CO3 with a charge of -2. And I can tell that I don't have enough positive charges. I need another ammonium ion to pair up with the carbonate to get the formula NH4, 2, CO3. Because there were 2 ammonium ions, that is in parentheses. We've now learned everything we need to know about naming ionic compounds, but we learned each step in isolation where we knew exactly what the tricks were that we needed to look for. The challenge is being faced with a variety of ionic compounds and knowing the right rules to look for when. So in the next segment, we need to practice a mix of different kinds of ionic compounds and getting the names right. I hope this helped.